Ladies and gentlemen, welcome to the second talk of this session. The speaker is Professor Amir Mohammadi from University of San Diego. He will talk about dynamics in homogeneous spaces. Let's welcome him.
Thank you. Thanks very much for the invitation. It's great to be here. It's my first time in China, and it's been great so far. So, well, before starting, I should apologize to some of you who have heard this talk very recently, and some of you who have maybe heard a version of this, but assuming that the audience is broad, I am going to give a survey. So that's what this is. All right, so most of what I say is joint with Ellen Lindenstrauss and Jiren Wang and Lei Yang, and some of it's also joint with other people. I will mention as we go. So I'm going to start with three basic examples, which in some sense, okay, some people may disagree with this, but I think a good number of people agree that they have been the reason this field of homogeneous dynamics has become popular. The examples are going to be in number theory and geometry. I'm going to start with the first one, which is a conjecture of Oppenheim in his thesis in late 1920s. So he was motivated by the famous Mayer's theorem that if you have a rational form in 5 or more variables, if it's indefinite, then it represents 0 over Q. He wanted an irrational version of this. Most of this talk is going to be about these objects that are irrational objects from number theory. There will be at one point that I'll pause and talk about rational objects for maybe 5 minutes, but most of the time I'm talking about irrational objects. So let's take a quadratic form, so a homogeneous polynomial of degree 2 in 3 or more variables. Here is one example that I've written here. And I'm assuming that it's not a multiple of a form with integral coefficients. And Oppenheim was asking whether it's possible to have arbitrarily small values as the output of this form, or more generally, if I evaluate the form at Z3, the integral lattice, is it true that the values are going to be dense? So this is not exactly what he asked. He asked in 5 or more variables, but soon Davenport realized that it's actually true. It should be true for 3 or more variables. He didn't ask about density, but I think one can imagine that that's what he had in mind. And just a remark that 3 or more is optimal. You cannot hope to have this result for 2 forms in 2 variables because there are numbers with bounded continuous fraction expansion. For example, this form that I've written here is one example that tells you you cannot have this result in 2 variables. So this is a question in number theory that remained open for quite some time until in mid-80s, Margulis used dynamics to solve it. Before Margulis's proof, there were cases with many variables using circle method that they were solved, and Ivanich had some results for forms in signature 2-2, some special forms, diagonal forms in signature 2-2 using sieve method that he could resolve. But to this day, the only solution that addresses the general form is dynamical. There is no proof using number theory in 3 variables. And I just want to maybe hint at how one would go about addressing this question using dynamics. Why quadratic forms and not cubic forms? The reason one looks at quadratic forms is that, okay, we look at problems that we can solve. So quadratic forms, they come equipped with a huge symmetry group. So in 3 or more variables, the isometry group, the symmetry group of a quadratic form is a complicated group. In 3 variables, it's basically SL2. SL2R, this is a complicated group, and my problem has this huge symmetry group. If I am interested in evaluating the form at integer lattice, I can move it within this entire group and evaluate the form at the values of integral lattice moved around with this isometry group. So using this point of view, already Castles and Sonata-Dyer had realized that this problem translates to a question about action of this group on certain space of lattices, space of unimodular lattices in R3, which one can identify with SL3R minus SL3Z. And this was also made explicit by Raghunathan, who actually formulated the conjecture about action of groups of similar nature. We'll come back to it later. That if one can understand this action very well, somehow beyond the usual dynamical questions of what happens to a typical orbit, but what happens to this particular point in this space. The standard lattice is a point in the space of lattices in R3. So these are discrete subgroups with covolume 1 in R3, and Z3 is one of them. And I take this and move it around with this isometry group, and the question is, where does it go in this space? Is it true that it will be an unbounded orbit in this space, which is not compact, but it carries a finite invariant measure? Is it true that it's unbounded unless the form is an integral form? And this is precisely what Margulis proved. Margulis proved that you start with this standard lattice, you move it around with the isometry group of the form. This orbit is either compact or the form is irrational. If the form is irrational, then the orbit is not compact. This is what he proved, and hence followed the Oppenheim conjecture. There were generalizations by Margulis and Danny, and later the problem was addressed in full generality by Ratner, but we'll get to it in a minute. Let me pause here for questions, because I'm going to now go to another question. Thank you. Thank you very much. So this space, the space of unimodular lattices in R3, okay, so you have a lattice, and you can imagine what compactness means. I have a basis. If the basis converges to another basis, then I'm converging in the space of lattices. How can I go to infinity? I can take a vector and shrink it. Of course, this space there are more complicated ways of going to infinity, but essentially, when you go to infinity, Mahler's compactness criteria will tell you you have a short vector. And if you have a short vector, then the value of the form is small. Thank you very much. Any other questions, comments? Which one? That being... So you can have a rational form that also has an unbounded orbit, right? You can have a rational, if your form represents 0 non-trivially over Q, then you can have an unbounded orbit. Being dense versus being closed, that's equivalent. So if you have, thank you. If you have a quadratic form Q whose coefficients are rational, then the orbit is going to be properly embedded submanifold in here. And this is equivalent to being rational or irrational. Thank you. Any other questions, comments? All right. So that's question 1, which we know the answer, but for pure surface purpose of self-promotion, here's a question that you have a qualitative version. Given epsilon, there exists a vector. A natural question you can ask is, given epsilon, how big of a vector do I need? And I want to come back to this. Second question, which still even in the qualitative form, it's open, is the following question, around the same time, formulated by Littlewood, that asks about approximation, this time of linear forms. So it's product of 3 linear forms. I have 2 real numbers, alpha and beta, and I want to show that for every epsilon you give me, I can find n, m1, and m2 so that this expression is less than epsilon. So when I approximate alpha with a rational number, beta with a rational number, then I don't need too big of a denominator. That's basically what this question is asking. Again, similar to the previous case, you cannot hope to drop beta and have this for all pairs alpha beta. Again, as is often the case, if you're only interested in knowing typical behavior, the behavior of almost every point, this is an easy question, was already answered by Finchin in 20s, this is the easy direction of hinging, indeed. The harder direction is the other direction. But if you want to really have this for all pairs alpha beta, you really need two of them. You cannot have for one vector. So again, I have a question in number theory. This time, rather than having a form, having a quadratic form, it's product of linear forms, and I want to know whether I can find n, m1, and m2 so that this happens. The question is clear? Okay, and I want to now translate this to dynamics. Again, I want to look at symmetries of this form. So let's write this in the continuous form. So here is the form, product of three linear forms, z, alpha z plus x, beta z plus y. And obviously this has a big symmetry group, not as big as the previous case. The symmetry group is somewhat simpler. It's an abelian group. I can multiply two factors by two real numbers and then divide the third one by the product of those two. So the group of there's a two-dimensional abelian group that acts on the problem. And again, I can move the problem. I can move the lattice that corresponds to this problem. In this case, this is the lattice in the space of lattices with this isometry group. And going back to what Bassam pointed out, because going to infinity means you have short vectors. If I can show that this orbit goes to infinity, I have found short vectors in this lattice under this action. And as a result, product of the coordinates is going to be small. So I will be able to solve Littlewood conjecture. This we don't know yet. But there was a spectacular progress by Einsiedler, Ketag, Lindenstrauss, one of the works that was cited in Lindenstrauss's Fields Medal citation, that the set of possible exceptions to this has Hausdorff dimension 0. And the way this was proved was, again, by studying the action of this two-dimensional abelian group on this space and understanding it, again, beyond the usual questions answered in ergodic theory, trying to understand all measures that are invariant under all probability measures that are ergodic and invariant under this, under some extra assumption of positivity of entropy, they can show that such a measure has to be Haar measure, and this is the Liouville measure, and this implies the progress towards Littlewood that I mentioned. So again, the question becomes the action of a group on a homogeneous space, SL3R mod SL3Z in this case, and one wants to understand behavior of every orbit, not almost every orbit. And the fact that this is a two-dimensional group is crucial. If you took one-dimensional group, this action has many invariant measures. This was already known in some cases. I think goes back to maybe Ornstein and Weiss. Some most general case, if I am not mistaken, Adam has a result in this direction, that the action of one-dimensional group, one-dimensional diagonalizable group is Bernoulli, and you can't expect any sort of rigidity of this type. Okay, any questions about this? That's a good question. Topologically, yes, but no. So I think topologically, it's, at least I believe that this statement is true, that the orbit that is, if it's not a periodic orbit, it has to be bounded. But whether or not the only invariant measures are measured, this is a different question. Yeah. Thanks. So two problems in number theory related to homogeneous dynamics. Now I want to maybe mention something beyond homogeneous dynamics, but this talk is not going to be about this space. We're going to return to homogeneous dynamics. Unboundedness, yeah. Correct. Yeah, but what I'm saying is I think topological question one can believe. The measure question is a harder question. I don't know if is going to be this. Yeah. That bounded orbits, they correspond to the orbits. Yeah. And well, I think it was hinted at, and I should have mentioned, this is closely related to the famous conjecture of Furstenberg times 2 times 3, that if on the circle, you have a measure that's ergodic and invariant under times 2 and times 3, then you should know what it is. And if entropy is positive, then we know this is Lebesgue. If not, this is wide open. Topological question was answered by first American solve in that context already in the 60s. Okay, and here is another instance of questions that have motivated this type of questions that I am going to try and address later in the talk. And this one is beyond homogeneous spaces. So I want to play billiard on a polygon whose angles are rational multiple of pi. And, well, you can play billiard in a rectangular billiard table, but that's maybe boring. I want to play it in this L-shaped table. And then I want to ask how many periodic paths there exist of length less than or equal to t. Of course, the answer is infinitely many, uncountably many, because as soon as you have one, you have a cylinder around it that also is going to be periodic, but I'm really counting the cylinders of periodic orbits. So I start at a point, I shoot the ball, angle of incidence is the same as angle of reflection, and then ask how many periodic orbits there are of size bounded by t. And conjecturally, this should behave quadratically. We know that for a rectangular billiard table, this is basically the basic lattice count problem, and it grows quadratically. Conjecture is that it should grow quadratically. Also in this case, upper and lower bound are known. They have been known since mid-80s, thanks to Howie Mazur, that there is an upper bound which is quadratic and a lower bound that's quadratic. But asymptotics are not known. To the best of my knowledge, there isn't a single table that's not lattice surface that we know the asymptotic. It's what is the? But okay, that's also cheating. Something that's branched over cover of this and that. That's something that's genuinely yeah. So, and this problem, we only know it on average. And this is the best we know. We also know it for almost, so this problem translates to, the reason we can even handle this problem, the reason we can even have an answer of this type is the close link to Topological dynamics. And that's where this rational multiple of pi comes into the picture. So rather than reflecting the trajectory, I can reflect the table, and then in this case, if I do that, this is what I'm going to get. And now I can identify the opposite sides which are parallel, and what I will get is a Riemann surface. In this case, if you do that, then these points are all going to go to one point, and the corners, these four corners are going to go to one point. These four corners are going to go to one point. And as we all know, if you have a Riemann surface of higher genus, it cannot carry a flat metric. And in this case, I'm going to have a surface of genus 2, so it can't carry a flat metric. But the metric that I have on C, dz, is going to descend to a metric. So where does all the curvature go? All the curvature will go to these coin point singularities. In this case, those 4 points, each of which has angle 270, is going to get identified. I'm going to have one point with too much angle 6 pi, and every other place I will have a flat metric. So this is the type of object that I'm going to get, a Riemann surface together with a singular flat metric. And the billiard paths will give you straight line flow in here. And then you can try to now, rather than counting periodic trajectories, the problem translates to counting these straight line flows, periodic orbits for these straight line flows. And you can try to study this problem. This space, the space of such object, Riemann surfaces equipped with a singular flat metric, these have a natural SL2R action because each of them is given by a polygon. SL2R acts on R2, so it acts on polygons. The combinatorics of this space is fixed by this SL2R action, the number of singularities, and SL2R action is exactly the group which is going to preserve what's called a saddle connection. So it acts on this space, and now you can ask a similar question, that given an object of this type, what are the SL2R orbits, orbit closures of these points? And questions of this type have been studied, and they're difficult questions. We know answer to SL2R orbit closures, and as a result, we know something like this, but we don't know finer answer to finer questions, hence we don't know the asymptotic. And now after you have translated this to this, after you have translated the problem to this question, now you can ask what happens to almost every flat surface. That question was studied by Maser and Eskin, and there you have an asymptotic for almost every flat surface. However, the billiard tables, they form a codimension 2 subset in this space. So even if you're only interested in knowing what happens to almost every billiard table, almost every answer here is not going to tell you what you want there. So we don't know this for almost every table, this asymptotic. We don't know it for almost every table. All right, and so that's another set of questions that have been studied extensively over the past maybe 20 years or so, with some spectacular result due to Eskin and Mirzakhani, but still the picture is not complete there. Okay, that's the third question. Any questions about this? All right. So the rest of the talk, I am going to discuss maybe rigidity results that I alluded to in greater details and somehow explain where we are and what the next steps are. What are the type of rigidity results that I'm after? So the type of rigidity results are these results that we have learned maybe in, I don't know, at some point everybody has heard this. You have a 2 torus, which is R2 mod out by Z2. You have a line in R2, then you know what the image is. Either it closes up, or if this is an irrational line, it's going to fill up the space. This is the type of rigidity result that I would like to have, that I understand orbit of every point, and not only the orbit of almost every point. The first result in this direction goes back to Hedlund from mid-30s, that he looked at, and I want to, okay, I already described what happens in the commutative world in the torus, but I would like to look at more complicated groups, the groups of 2 by 2 matrices with determinant 1, or n by n matrices with determinant 1, more generally simple Lie groups, and objects like the torus that you can construct using them, which is you take this group and mod out by some discrete subgroup of it. So Hedlund looked at a question of this type. You look at a, let's say, a compact surface of genus 2 or bigger. Then this one, the universal cover is going to be H2, hyperbolic space. And then you ask what happens to analogs of straight lines. So there are two, well, at least 2 things you can do. You can take analogs of straight lines with curvature 0, which are geodesics, or you can take Euclidean objects, curvature 1, sitting there. And Hedlund correctly looked at what happens to horocycles, these curvature 1. So these are circles resting at infinity in H2. And then you can ask what happens to this when you go modulo the fundamental group. And the answer is that exactly the analogous statement to the torus happens here. Either this circle is going to fill up your entire space, or if it's not, then there's an algebraic reason for it. There's a geometric description for what happens. It's going to bound a cusp. And why should you look at this? Because if you don't, and look at the geodesics, which have curvature 0, then these are very chaotic. This corresponds to geodesic flow in this space, and as I already mentioned, this is Bernoulli. You can't expect anything like this. The only obstruction you have is dimension. You can have something that closes up, you can have something that stands, but you can have any fractal behavior in the middle that you can have. So this is the correct context for which you can expect strong rigidity result like this, and already Hedlund answered that. This was generalized later by Furstenberg, Danny, and others. And a similar result can be proved if you replace, so this was fun if you go to the group language, because SL2R mod gamma is the unitangent bundle of this space. In the group language, that's the type of orbit you are looking at. And now you can say, what if I replace this by n and replace this one dimension by the full upper triangular group? Similar results can be proved. Slightly harder, but not very difficult. The reason for this type of question not being very difficult is that this is the full unstable for some flow. So the L2 theory is going to help you understand individual orbits. I'll come back to this. Now, you can ask, okay, what's the big deal? What if I change SL2R to SL3R mod gamma and keep the one dimension? I don't want to go and look at a much bigger group, the group of full upper triangular group, but I just want to have a one-dimensional flow on this space and ask for a similar result. You can ask. There's nothing wrong with asking the question. And this problem is infinitely more difficult. This was indeed conjectured by Raghunathan, and it took some time and several brilliant mathematicians to give complete answer. The complete answer was given by Marina Ratner. And this is celebrated theorem of Ratner, that you look at a Lie group, you look at a lattice, a discrete subgroup with finite covolume, and a one-dimensional subgroup that looks like this, which is obtained by exponentiating a nilpotent element. Then I start from any point in the space and I look at the long orbit under this one-dimensional group. Then the space average, the time average along this orbit converges to space average. But space average, it can't be the space average of the whole space, because this is a highly non-uniquely ergodic system. There can be intermediate behaviors, but the next best thing that can hold, that one can hope will hold, holds. That you give me a point, then there is an intermediate, possibly intermediate submanifold that this one-dimensional orbit is going to fill up this intermediate submanifold. And all these intermediate submanifolds are themselves homogeneous subvarieties. They are given as orbits of some subgroups. So there's a subgroup containing your one-dimensional group contained in the group, so that X has a periodic orbit and the time average converges to space average with respect to this. So this is a very beautiful, very complete solution to understanding orbit of individual points under unipotent flows, which was given by Ratner in the 90s. Any questions? Okay. No, highly non-uniquely ergodic. Non-uniquely ergodic. There are many intermediate behaviors. The only really case that this is uniquely ergodic is this case of compact orbits of SL2R. Yeah. And okay, as it is the case with any deep theorem, this has a long history. Raghunathan conjectured it in topological context. What's the orbit closure of every point? If you know equidistribution, of course you know orbit closure, but there was an approach using topological dynamics by Margulis that I already mentioned in the context of Oppenheim conjecture, and this was an active program when Ratner proved her theorem that somehow using minimal sets and topological dynamics, one can try to answer this version of Raghunathan's conjecture. Now it's actually believed that that could have been completed, but okay, the measure approach is better approach in some sense. Okay? So, and I already mentioned that prior to all of these cases of generalizing horocycle flow to the case which is called horospherical flow, these were studied. Danny had results in this direction. But one-dimensional groups are just harder. Okay? The rest of the talk basically is going to be about these groups generated by unipotents, but I need to include this because motivated, inspired by Ratner's work and Margulis's work, many people have tried to prove rigidity results of similar nature for different groups. If you don't take W, this acting group, to be generated by unipotents, but maybe it's a multidimensional diagonalizable group, this is still wide open, as I mentioned. Some special cases were studied by Lindenstrauss, Einzidler, Ketag, Lindenstrauss, and then Einzidler, Lindenstrauss. We have understanding of what happens under the additional assumption that there is some positivity of entropy, but entropy 0 is beyond reach. We don't know what to do. The case of maybe you don't have a continuous group acting. Maybe it's a group generated by two matrices that they generate a free group. So random walks on these spaces. This has been studied. The case of action on beyond homogeneous spaces, translation surfaces, the space of translation surfaces that I mentioned, this has been studied extensively. There is a very recent result trying to generalize this to basically everything by, let me see if I can reproduce the names, Aaron Brown, Rodriguez Hertz, Alex Eskin, and Simeon Philippe, that they study random dynamics on symplectic manifolds, or more generally in the context of smooth dynamics, but this is still, the picture is very not complete. So we are not there, and I will be and have been talking about finite volume manifolds, but you could ask what happens if you keep gamma to be discrete and maybe interesting, Zariski dense, but you don't take it to be finite volume. Like in the context of Kleinian groups, you have a maybe geometrically finite Kleinian manifold, hyperbolic 3 manifold, and then you ask what happens to geodesic planes in here. This also has been studied. This is a list that, okay, the criteria to make it to this list has been either you have been an award or you're the speaker. So this is somehow, it's a very, very selective list and very biased list, admittedly. So there have been many other spectacular work which I have not included here, and I apologize, but this is just a list. Okay, so that's essentially the state of the art for qualitative results. Any questions before I move on? All right, so no questions.
Is it known when there's theory falls?
For which one?
If you take hyperbolic treatment.
Oh yeah. So thanks for the question. If you have gamma, so it's if and only if statement, in some sense yes, in some sense no. So let me give an answer. You take SL2C, so hyperbolic 3 manifold, and you take it geometrically infinite. I know nothing. Geometrically finite. If you take a geometrically finite in it, if it's acylindrical, then an analog of Ratner's theorem holds. If it's not acylindrical, then counterexamples can be constructed, but we also understand where the counterexamples come from. So there is flexibility, but we know why there is flexibility when it's not acylindrical. I have conjectures, but I don't know how to prove. Yeah, I think it's so. For example, the doubly degenerate case, there should be some analog of Ratner's theorem, but it's not clear. Yeah, thanks. But the case of acylindrical manifold, the picture is pretty complete. You understand it? It's essentially there is rigidity. Thanks. So now I want to go beyond. Okay, we understand the picture qualitatively for unipotent flows. You can ask, how about quantitative results? And these are, okay, they're interesting on their own, but they're also interesting because of applications, possible applications to number theory, which hopefully I will hint at some of them as we go along. So what's the type of question that I'm asking? So Ratner says you start at a point, at any point, then the long-term behavior is understood. It's the orbit accumulate on some intermediate submanifold. Now, what the kind of question I want to ask is that I don't want to wait forever. I'm going to go up to time t, and I want to know how much of the space I fill up. Or going back to my first slide, you give me an epsilon. I don't want to just show there exists a vector so that the value of the quadratic form is less than epsilon. I want to show there is a vector whose size is not too big in terms of epsilon so that the value of the quadratic form is less than epsilon. This is the type of question I want to ask. And these also, somehow, they have been sought after for some time with some success, which I will mention in the next slide. But just before going there, I want to maybe point out that questions of this type usually are difficult. And they're difficult by the very nature that different points can have different behaviors. And you need to make sure your point is not too close to something with bad behavior. Already we know this for irrational rotation of circle. If your angle of rotation is rational, you have a periodic orbit. If the angle of rotation is Diophantine, then you know there's good equidistribution. Somehow the intermediate behavior can occur depending on how well of an approximation you have for the angle of rotation. Here's an example in the continuous form. You take the two torus, and then I look at this line, and I want to know how much of the space it fills up. So what we know here is that this orbit is going to close up. It's going to give you a circle. Now, I look at this line, which is almost horizontal. So if my observer is living on this line, it's going to take it for a long time for it to realize that it's not horizontal and it needs to go up and fill up the whole space. For example, if I catch it at half the life that it needs to make it all the way to that corner after modding out by Z2, all I see is half of the torus. And this is the type of question that, this is the type of problem that you are going to encounter if you want to have quantitative results. Okay? So this is just to justify the fact that when I stated theorem, the theorem is going to be complicated. So you don't, it's not because we are lazy, it's just the way it should be. Okay. So what's known in this context? The earliest results are in the context of maybe toral, the action on the torus, or more generally, nil flows. So rather than looking at quotients of SL3R, maybe I want to look at quotients of a group that is like Rn mod out by Zn, or maybe a group that looks like this, X, Y, Z, and then I mod out by the integral version of that, M, N, Q. So the Heisenberg group mod out by a lattice, and then you can ask what happens to one-dimensional flows. Here, questions of this kind they naturally are linked to understanding, say, arithmetic progressions in primes, and they were studied by Green and Tao in their analysis in this direction. And very beautiful answer exists that you have analog of Ratner's theorem with a polynomial rate, polynomial error rate. Huh? What the power? I just mean power. Yeah, it's not an integer power. Yeah, it's less than. It's very small. Yeah, no. Fractional polynomial. That's the terminology. So for me, polynomial is, so I go up to time t, and I like t to the minus epsilon. This is polynomial. That's and you make this epsilon better. It's never better than one. It's, yeah. And well, okay, I am going to get to that in Sarnak's work here, but it's the well-known Riemann hypothesis is related to a rate of this nature when you can put 3/4 for the horocycle flow. But okay, we'll get there. Okay, so this is the case of Green and Tao, where you look at quotients of unipotent groups by discrete subgroups, and you get polynomial, fractional polynomial rates, but the proof really relies on the fact that you're working with unipotent groups. The proof is an inductive scheme trying to decrease the degree of nilpotency and bringing it down finally to the abelian case where you can use Fourier analysis. So that's how this proof is goes. There has been some, I think, more recent developments trying to improve on dependence on the dimension or the degree, but okay, that's not the point I want to raise here. The proof does rely on the fact that you're dealing with a unipotent group, and that's the point I want to convey. Yeah. Yeah, of course. Is somehow thanks. This is also a highly non-uniquely ergodic system. So the question is your base point. How close is your base point to a periodic torus? Yeah, absolutely. Other case that has been studied successfully is the case related to these horospherical groups that I mentioned, or closely related to it. You have a stabilizer of an involution in a simple Lie group, for example, SOPQ inside SLN, or maybe the symplectic group, stabilizer of some involution. These are called symmetric groups, or I call them symmetric groups. And here also there has been plenty of results with very good rates, in this sense polynomial rates of EQ distribution. And the reason for this is that I think I alluded to this before. These horospherical groups are full unstable foliation for some diagonal group, for some geodesic flow, and you can use L2 theory to get pointwise estimate. Essentially, in all of these works, with the exception of these last two, which I will remark on, if you look at the proof, there is an L2 estimate, and the L2 estimate is giving you pointwise estimate. And I should mention Sarnak's work, as Sam was pointing out. Sarnak, in particular, what he looked at, this is a paper in the 80s, you look at a closed horocycle, and you push it down in the modular surface, SL2R mod SL2Z. And then you want to show that this equidistributes with a rate that is polynomial in the length of this horocycle, of this long closed horocycle. What is 10? I have 10 minutes. I have 15 minutes. Yeah. And okay. And what he proved is that you have equidistribution with a rate that is square root of the length. If you can do minus 3/4 of the length, that's Riemann hypothesis. This is an observation by Sarnak and Zagier, but okay, this is not the correct approach in a sense to prove, or not believed to be correct approach to prove Riemann hypothesis. Another work in this direction is in the context of random walks by Borgian, Forman, Lindenstrauss, and Moses. You look at two non-commuting allomorphisms of the torus, and you want to know the behavior of every point. The ideas used there are additive combinatorics. There's two other class of examples that have been studied. I mentioned that for the most part of this talk, I am looking at irrational forms. What if you want to study distribution of points under the rational form? This is somehow, it's counterintuitive. We should not be able to use dynamics to say something about finitely many points, but we can. This is this idea of, that goes back in a sense to work of Venkatesh and Ellenberg, that you can use dynamics to say something in the context of local to global principle for rational quadratic forms. These involve understanding behavior of long periodic orbits coming from these rational forms, and they have also been studied extensively, starting with influential work of Einzidler, Margulis, and Venkatesh, that you look at a periodic orbit in quotient of a semisimple group by some arithmetic subgroup, really congruent subgroup, and then you want to show that these periodic orbits equidistribute with a rate that again is polynomial in complexity of this orbit. the volume of this orbit. If you're looking at quadratic forms, discriminant of this quadratic form. The bigger the discriminant, the more complicated the form, and I expect equidistribution with a rate like this. And these have been also studied and successfully answered. The deep input is this Clozel's property tau that comes into the picture. When you look at these periodic orbits, this gives you a possibly infinite collection of closed orbits, but they all have a uniform spectral gap. And you can leverage this to get some equidistribution result with a polynomial rate. Now, beyond this, if you don't have any of these tools that I described, the general case, somehow the general proofs by Margulis and Ratner, they're not effective and very difficult to effectivize. And effectivizing them usually does not give you polynomial rate. Not that usually, it will never give you polynomial rate. The best you can hope for is an iteration of logarithms. So we had been searching for alternative proofs, alternative approach to understanding flows, unipotent actions on homogeneous spaces, and the understanding was that there should be some tools from additive combinatorics, incident geometry that can help, and this indeed proved successful. So in the next 5 minutes, I will just maybe I will be able to state maybe the theorem. So the theory is well developing, thankfully fast, but the picture is not complete yet. I'm just going to give a few examples that, and this is not the most recent examples. It's I think the picture has changed already 2 weeks ago, but I will just stick to this list of examples. So take G to be one of these groups, SL2C, product of two SL2s, or SL3R, and I want to look at a certain one-dimensional unipotent subgroup inside this. Let's just take the case, the third case, which is related to the Oppenheim conjecture. And so in this case, the diagonal group that I'm going to look at is e to the t1, e to the minus t. The unipotent group that I'm going to be looking at is 1, 1, 1, r squared over 2. And that's really the terminology that I've written there. This is exactly what you're going to get. So you take the isometry group of some quadratic form in signature 2, 1. The image of this one-dimensional unipotent and diagonal group are going to give you that. So these are the two groups that I am looking at. So I have, this is G, that's H, this is what I'm going to call A sub T, and this is what I'm going to call UR. And I'm going to give myself some gamma, which is an arithmetic lattice, and arithmetic just means take SL3Z. So G is SL3R, and gamma is SL3Z. This is what it is, and I'm looking at the quotient. And I want to study orbits of this object, orbit of every point under this object. But rather than doing that directly, I'm first going to look at an orbit that looks like I apply time 1 of the unipotent and increase entropy using AT. And I want to see what I can say about these orbits. So there is some language here, which if I have time, I will return to. But in the cases that I am looking at, you don't need that language. The Lie algebra here is 8-dimensional. This is 3-dimensional. The complement is a 5-dimensional irreducible representation of SL2R. That's what you should keep in mind. Okay? So here's the theorem. What is the theorem trying to say? It wants to say that either you have equidistribution with a polynomial rate, or the reason you don't have it is an obstruction of low complexity that was too close to your point, which prevented you from equidistribution. Just like this picture of the torus. If I don't have equidistribution, there is a closed circle near my orbit that the orbit is just too close to it. It doesn't have time to go fill up the space. So that's how the theorem should look like, and that's how the theorem looks like. So what is it saying? You give me a test function, and I look at the average of this test function under this particular flow. What is the flow? I apply time 1 of the unipotent, as I mentioned I would, and I increase entropy by flowing it with a large diagonal, a log t of this u01x. 0. So this is not a long unipotent orbit. It's a long unipotent orbit from a different base point. That's what it is, but this is what I want to look at. Next slide will explain why this is related to long unipotent orbits. So that's the type of average I'm looking at. And the theorem says that this is close to the space average with a rate that is polynomial. There are two parameters here, t and r. And in first reading, you should just take r to be t to power epsilon. So r is a small power of t, so this is really a polynomial rate in t. Or, if it's not happening, the reason for it is that there was a periodic orbit of this SL2R, that my point was just too close to it. This entire orbit is as if it's trapped there, and it just doesn't have time to go fill up the space. And this is the best you can hope for with the exception of this power kappa, because the length of the orbit is t. Length of the orbit being t, you cannot hope to fill up the space at more rate than polynomial. So this is the best you can hope for. You can of course hope to improve kappa, which we cannot, but we are happy to get some positive kappa. That's the result. Any question about the statement before I run out of time?
Different t could be different.
Yeah. These two are not even mutually disjoint, right? Because you can be very close to a periodic orbit of a large volume, and that itself becomes equidistributed. But this is always the case in this quantitative world, right? You can have a large circle that is almost filling up the space, and your point is also very close to it. Yeah. Certainly. So maybe I will make some remarks. So I started at 2:15. I'm supposed to end at 3:15. I'll end at 3:10, right? So, This is one of the remarks. Remark number 0. Now, maybe more important remarks. So the program started with some density result with the loan, some equidistribution result for the case of SL2CN product, and now we are able to address this case of. So I wrote 3 examples. There are 3 other examples, SP4, G2, and SU21, that we can address, and all of them, as of the results that I'm writing here, it's related to this decomposition, that Lie algebra of G can be written as Lie algebra of H and some irreducible representation of SL2R. And this is the cases that I have written here. There was an important case addressed by Lei Yang, the case of reducible SL2R inside SL3R. And very important and impressive work by Wei-Kun He and Timothy Bernard in the context of random walks on homogeneous spaces. I already mentioned the work of Benoit and Kahn. This is effectivizing that work and actually proving something that without this effective work, we didn't know it even in the qualitative work. So it relies on similar ideas of using incident geometry, but it's a beautiful work. Let me, before going to, well, I should actually say this because I want to mention this. So I stated Ratner's theorem for long unipotent orbits, but I stated this for pushes of time 1 length, unit 1 unipotent. The reason for this is that when we are proving this, we want to use language of random walks to somehow improve dimension gradually. And this type of flow does behave like random walk. But you might be interested in knowing what happens to long unipotent orbits. In the homogeneous context, there is this beautiful machinery developed by Danny Margulis and Nemish Shah, which is called linearization technique. It allows you to go between the two. Basically, if you know the result for one of them, you can prove the result for the other one. And that's indeed what we can do. After we have this theorem A, you can use that to translate it to a result about long unipotent orbits. And this has had spectacular application in a recent work of Giovanni, Adam, and Maxime to sparsity distribution for horocycle flow. So I started basically the talk by saying let this act on SL2R mod gamma, and then you have effective EQ distribution, or you have EQ distribution. What if rather than taking T to come from in the continuous time, I take it to sample along primes? This is a conjecture of, well, I think I can say it's a conjecture of Sarnax, that these should behave like the continuous version. If the continuous version EQ distributes, these should EQ distribute. This we don't know yet, but they can prove you can let T be 2 primes, product of 2 primes, and you have EQ distribution. And for this, they need this case of product of 2 SL2s to answer this question. I will end by answering the question that I asked in the beginning, that thanks to theorem A, we can now answer Oppenheim with a polynomial rate. If you want your vector, you want the value to be less than epsilon, assuming your form has some Diophantine condition, the vector you need is 1 over epsilon to some power, depending on these Diophantine conditions on the coefficient. Okay, I'll stop there.
Thank you very much for this beautiful talk. Is there any question?
Your theorem required absolute rank at least 2?
Absolute rank exactly 2.
Exactly 2.
And yeah, thanks for the question. This shouldn't be required. At the moment, the tools, so the main, the proof uses tools from incidence geometry to improve dimension. Thanks for bringing this up. And the main ingredients from incidence geometry is this beautiful projection theorem due to Gang, Go, and Wang, some earlier versions due to Kahn-Markey, Orphan, and Vignari. And this result, this is too strong of a projection theorem. It's an optimal projection theorem. And in order to be able to apply this, we need this complement to be an irreducible representation. This is basically the action of the unipotent of SL2 on an irreducible representation. And this is the reason there is this restriction. This should be removed and will be removed soon.
Is the rank 1 case like trivial, or is it like, are there published versions of that?
Rank 1, what's the action? Of
like horocycle flow, like the horocycle flow on Gmod gamma.
So your group is SL2R or your group
SL2R,
is SPM?
SL2R.
SL2R, okay, this is okay. This
this
is the horospherical case, yeah.
It should be true, but I haven't seen this before.
It exists in the literature. Yeah. Yeah, this is. Oh, this is that's so. The case of SL2C is what I mentioned. This is absolute rank 2. This is the case. But if you look at SO41, this is the case that we cannot yet handle. And the complement, so you take this SL2R inside it, which is SO21. The complement has 2 irreducible components. And that's the case that should be handled, but is not handled yet. Yeah. The case of horosphere, okay, I take it as known. Yeah.
So I don't know if this makes any sense, but what about Oppenheim conjecture if you just evaluate at primes? So instead of 3 integers, 3 primes.
Yeah, I don't know the answer, but this I think is a very good question.
So this is expected to be.
Okay, I won't conjecture, but it's a very good question. Yeah, what if you take the value at some discrete points? And, some sparse points.
But so these quantitative results don't shed
No,
any light.
not at the moment. No. Yeah, thanks.
So, like in the intermediate case, it's simpler. Like here, the full unstable is 3-dimensional. You do 1-dimensional. Is the 2-dimensional case simpler than 1-dimensional? Like in general.
Thanks. That's also an excellent question. In the case of SL3R, this did not feature, but in other cases, it will feature. Actually, one of the cases that we hope we'll be able to handle soon is you take a simple group, you take a 1-dimensional unipotent, which is regular, and you take centralizer of this. This is related to this work of Paul Nelson and Akshay Venkatesh. They need exactly this, and this case we are hopeful that we can. Yeah, thanks.
Any other question? Okay, let's thank the speaker again.